So this is the expected thing. All right, we have an exam next week, next Wednesday, and nothing that we do today or Wednesday or this Wednesday is on the exam, and so of course things clear out a little bit. But this is a mistake because of course this is going to be a big thing on the final, right? It's not going to be a thing on the midterm. I'll also talk a little bit about some stuff that goes on the midterm just as a review. Some people asked some questions. I thought, oh, okay, maybe there's a few things that people missed along the way. But this is going to be a major thing going forward, but of course not for next week. Okay? Now, the first thing I'm going to start out with is there any questions? So like today and Wednesday, and also like, I guess next Monday as well, we're going to do a review as well. If you have any review questions whatsoever, please do bring them. Looking around with my fuzzy old eyes. Anyone like, oh no, I want to ask, but I'm too shy? No? Okay. All right. So we did this thing with the two policies, right? And how there's no pure strategy Nash equilibrium in terms of choosing where the politicians are going to be. I want to do two things with this while we're here. So we started out. So we had our policy 1, we had our policy 2, and we put our 3 guys like this so that this was a contract curve, that was a contract curve, and that was a contract curve, right? And because they had different contract curves, you could go from contract curve to contract curve and steal a voter from the other guy, and so it never settled down. Now, that, I think, is the most natural way to draw it. Like if you have only 3 guys, that you're going to put them most likely in a triangle, but it isn't the only way to do it. So the one other thing we could have done, if we were just drawing it, and is to, again, the next page, we could have drawn it like this, where we had a guy here, a guy here, and a guy here. Let's call them 1, 2, and 3, just so they have names. It sounds like they're not imaginative names, but I did know a guy named 3. Okay, it was like Trey. Everyone called him Trey. So it's a thing. You can be called 3. Or Ender, depending on your, so we've got this. I've just put them arbitrarily in a straight line. It seems a little special, and personally, I think it is a bit special. But just to see what happens, if we did the contract curve between 1 and 2, it would look something like this. Right? If we did the contract curve between 2 and 3, it would look something like that. And let me do it in a different color. If we do the contract curve between 1 and 3, it will look something like that, or could, if they had similar, they're overlapping is how I'm trying to make it, that they all go over the same spot, right? In which case, none of that stuff that we did last time works. In which case, it really just becomes an ordinary linear thing, because you can think about it, if we're always going to be on the contract curve, we're always going to be somewhere on this straight line, right? And so we can represent this whole thing and take this straight line sort of down this way, just carry everything down like so, and draw it out as a linear thing, right? It's just where are we going to be on that line? If we're always going to be on a contract curve, we're going to be somewhere on that line. And so then we got the guys on the line. We got Mr. 1 here, 2 here, and 3 here. And it's just our linear thing from the original Downs model to begin with. So we put them all in a straight line. It really comes down to picking a spot on that line. Even if the line's at an angle, it's still just a line, and we can draw it as a line and all the usual stuff. And so then we get, since we have to be on the line, this guy is the median voter, and whichever policies we offer, he's going to be on the winning side. Okay. Now, I personally think this is a little special in the sense that if you're arbitrarily putting points down on there, like giving people preferences, them all being in exactly a straight line seems a little special. On the other hand, just to take the other side, if we're just sort of arbitrarily plotting points, sure. But if these beliefs are coming from somewhere, if there's sort of like a whole political discussion, whole political philosophies that are giving us these points, then on a line they're maybe not as arbitrary. Like putting them anywhere might be a bit arbitrary. And in fact, the political discussion might force them into a straight line. We could imagine, for example, that policy 1 is the tax rate, and policy 2 is the lower it is, the more things go to social programs. Right? Or the higher it is, more things go to social programs versus police and stuff, right? And we can imagine a political philosophy where those things, it's not even just look at the US, but a political philosophy where those things go together. That people that want high tax rates tend to also want more social programs, and they move together. And so then maybe putting them on a line like that, maybe a little constrained, but maybe capturing something as well. Okay? Now, for this to work, it needs to be on an exact line, and exact seems a little special. Like even if we have a whole political philosophy and the talk around stuff is one way, people got their individual weirdness, right? And so being exactly on the line seems to me special, but no, what do you think? And it's also possible that if you're just a little off the line, technically we have this whole thing with the 3 contract curves, but is it a big deal when it's such small differences? Maybe it has to be big differences before we should actually care, because obviously it's a simple model capturing hopefully something about a complicated reality. And if it's only off by that much, let it go, man. Right? So that's plausible as well. So this is a thing that can happen. Right? Another thing I want to talk about while we're here, which goes back to this original Downs model in the first place, we had 2 things which at first glance can appear to be contradictory. So one thing we had is we had the Arrow's impossibility theorem. And one of the main parts of the Arrow's impossibility theorem is where everyone's going to have transitive preferences, and we are going to have non-dictatorship. So one of the things that we want out of our political system is that one guy isn't the dictator. Right? We're all going to vote, and we don't want there to be a dictator. Okay? And then, totally kind of separate, we did this Downs thing with competition on the line, right? Where the median voter was always on the winning side. And it is tempting to say, look, isn't the median voter kind of a dictator? And we said, look, we got away from Arrow, but it seems on the surface that maybe we're ignoring one of the requirements of Arrow, which is that there's not a dictator. But here we're getting a dictator. And so I want to talk just a minute about that, what we mean by dictator. Right? So in Arrow, we have non-dictatorship. Which means there's not one guy who's always winning, right? But in Arrow, we're talking for any preferences, there's not one guy who's winning. So non-dictatorship is actually saying there exists some preferences where Fred doesn't get his first choice. Now, anyone who's watched Scooby-Doo knows that Fred always gets his first choice. But we can imagine there's a cartoon somewhere where Fred doesn't get his first choice. And that's the idea. So not that Fred doesn't get his first choice, but there's some preferences where he doesn't get his first choice. And so if we go to the Downs model, well, not even the Downs model, just the median voter theorem stuff, right? We're going to have our policy line. And then we're going to say, let's put our 3 guys. Let's suppose there's 3 guys there. And we say, OK, we have guy 1, guy 2, and guy 3. 2, 3. 2 is the median voter. Whatever policies are offered up, 2 is going to win. He's going to be on the winning side. Okay? But that's for one particular set of preferences, right? There's another set of preferences that I could have chosen where it's 2, 1, and 3, in which case 1 is the median voter. Right, so this guy Fred, this guy Mr. 2, he's not always going to be, for every set of preferences, he's not going to be the winning voter. It's given a set of preferences, the median voter is always going to be on the winning side. But it's not this particular guy is on the winning side regardless of the preferences of everyone else. Okay, which is, it sounds similar on face value, but it's a very different thing. Right, so it's like, if I'm the dictator, whatever comes up, whatever the current conversation is, I know I'm going to be on the winning side. Okay. As the median voter, it's this particular thing came up. Therefore, these are the preferences of everyone. Hey, it looks so happens that I'm the pivotal guy. I'm going to be the guy who's just, going to be on the winning side. But it doesn't mean that regardless of what everyone else thinks, I'm going to be on the winning side. Right, so in the first one, for example, if it was regardless of what everyone else thought, then moving guy 3, if guy 3 changed his preferences, guy 2 would still win. Okay, but that's not necessarily true, right? The fact that guy 2 is the pivotal thing depends on everybody else's preferences and where they are. That's just how he happened to be in the middle. Okay, people with me here? Okay. Okay. So seemingly, like if you're sort of glancing through it, it seems like these are inconsistent, but in fact, the non-dictatorship is a very, very relaxed thing. It's like really, as a dictator, whatever comes up, this guy's going to win. Whatever anyone else thinks, this guy's going to win. But the median voter is, given what everyone else thinks, this guy's always going to win. Right? But maybe they're going to think something else other times. Okay. Any issues? Okay. So now we want to come back to median voters, and we're going to, we went into this two policy thing, but we sort of had left this whole median voter thing behind, right? We said, like, given what everyone's going to vote for, what do the politicians choose to give us in terms of policy? But forget about that. Suppose like there's just some referendum that comes up. Who's going to win this thing, right? It's not even people deciding what to offer us. It's just, this is what happened, and we're going to deal with that. Is there anything like the median voter theorem, right? Because with the median voter, we put this thing down. Let me sort of remind you what we did in more detail. We had this single policy line. We put our guys on the policy. I put 5. Well, I got 6. 6 is fun. Now, let me put 7 to start it with. We got our 7 guys, and we said, okay, let's figure out who's going to be in the middle, right? So we've got 7 guys. We're going to have 3 on each side. So those 3, and the guy in the middle is our median voter. We got the same number of people to the left, and we got the same number of people to the right, and therefore, in any pairwise discussion, he's going to be on the winning side. Because everyone has these single peak preferences, and so farther away from their ideal is worse for everybody. And so whatever we offer, whether it's A and B over here, A and B over here, A over here, B over there, whatever, he's always going to be on the winning side of the vote. Okay? And that was our median voter theorem. Okay? We also had slight complications in the median voter theorem, where we had, say, put 3 guys here, and 3 guys here, and we counted, well, now we got 6 guys, so we get 3 on the left and 3 on the right, and there's really nobody who's the median voter. And so we get sort of this indeterminate range. Where we're not really sure what's going on in there. I'm being a little vague about what happens because honestly, we don't know. It really depends on the things being offered. But is kind of median voter-ish, but it's not a median. And we said that's a problem, but it's not that big of a problem because if we think about millions and millions of people voting, that indeterminate range is going to be really, really small. And so typically we just say, well, suppose there's an odd number of voters and not worry about it, because honestly, we're not too worried about it. It's small, right? Probably. Not if it's a small committee, but then you always put odd number of voters and you don't have the problem. All right, so that's what we had. And the way I want you to think about this for the moment is we have this line. And let me put our guys in again. 1, 2, 3, 1, 2, 3, 4. All right. So we've got this line. A line is a one-dimensional thing, right? There's one dimension. You can go left and right. That's all you got. You got no up, you got no down, you got no back, you got no forth, you got no future, you got no past. It's just one-dimensional, right? What I'm going to do is I'm going to take a point. Make it blue. A point, which incidentally is 0 dimensions. It's got no width, it's got no height, it's got no depth, it's got no time. It's a timeless, perfect pole. Ideal form is just a point, right? 0 dimensions. And what I'm going to do is I'm going to take this point and I'm going to move it back and forth until I have half the people, or I have the same number of people on one side as I have on the other side, right? So I just take this point and I try it here and I say, my God, there's no people on the left and there's 7 people on the right. I have not achieved my goal of the same number on each side. Right? And then I move it over here and I try it here and I say, well, there's 1 guy on the left and there's 6 on the right. I haven't achieved my goal. And I keep doing this until I get to here. And that's the thing. And at that point, I've got 3 guys to the left and I've got 3 guys to the right. I've achieved my goal. And there's only 1 point in this particular example. There's only 1 point that does it. And so that must be what our median voter, right? Okay. So we think about it that way. That's kind of the exercise we're going to be doing going forward, to do a similar thing, right? It's not the natural way to do it, right? Naturally, you just say, well, who's the guy in the middle, right? And you're done. But it's the same thing, right? It's just, now we're talking dimensions, so we sound smarter or like nerdier. But we sound something. We definitely sound something, right? So we could also do it with this one, right? We could take our point, try it here, and we got 6 people to the right, nobody to the left, so we haven't achieved the goal. And we can try it here. We got 2 to the left, we got 4 to the right, haven't achieved our goal. But we can also try here, and we've got 3 to the left, and we've got 3 to the right. We have achieved our goal. We've got the same number on the left, and we've got the same number on the right, right? But we could also try it here, and we've achieved our goal as well. Same number on the left, same number on the right. We can try it here. So in fact, in this particular example, there's lots of these points, lots of this farther left and right that we can choose that will get us the same number on the left and the same number on the right. And that's telling us that we got this indeterminate zone going on, right? Because there's lots of ways to do it. And so there's no one thing that's always going to win. It gets a little more murky, and right? People with me here? Okay. So now we're going to go to n policy dimensions. With, in particular, n greater than 1. And this is one of the things that's nice about math. And we're not going to do the math for this so much because some people have had vector algebra and some people haven't had vector algebra. It depends on your high school, I think. Just out of curiosity, who had vector algebra in your, did you see dot products? And yeah, a few of you guys. Okay? It's not a particularly hard thing. It's a very clever thing. We'll see a little bit about what it looks like. It's just a way of doing math without worrying about how many dimensions you've got. Right? So it's very clever, and it's not very hard. But most people haven't seen it just because, how they set up the programs. You can't teach everything. They teach some things. They don't teach other things. But if you get a chance to look at vector algebra, it's very much fun. Okay, so the nice thing about that is it allows you to do all the algebra and say, here we have an object that has a bunch of dimensions. Right? We have something, a mathematical object has lots of dimensions. We're not going to worry about the dimensions. We're just gonna like multiply this by that, knowing that we have this technique that allows us to do it for 2 dimensions or 20 dimensions, and it's the same math either way. Okay. I'm going to do, naturally, my graphs with 2 dimensions because I can. So we're typically going to look at n equal to 2, but we're going to graph. And we're going to do that for 2 reasons. First of all, you know my art skills. I can't do 1 dimension. 2 is going to be stretching it, and 3, forget about it, right? No one's going to understand what I'm drawing. And secondly, I have a small brain, and 2 dimensions is about all I can come up with. I can sometimes imagine 3 dimensions. I cannot imagine 5 dimensions. I doubt you guys can. John von Neumann famously claimed to be able to think in 5 dimensions, and I think everyone visualized things in 5 dimensions, and I think everyone agrees he probably could. Like he was very clever. That's not me, and that's a lot to ask a person for a 3rd, 4th year class. So we're not going to be thinking in 5 dimensions, but the math is for any number of dimensions. So pick the number of policies that you think are relevant. It doesn't matter. All of this stuff is going to be the same. So everything we do with 2 dimensions is the same as if you have 23 policy dimensions. Okay? Okay. Turns out it's different than if you have 1, though. Right? So 1 is special, but 2, 3, 4, 27, nothing special about any of them. We know this because the math is relatively easy to do, and you can just prove it. Right? Okay. Okay, so we're going to have our 2 policy dimensions, and let me draw this out. I'm going to put just for fun, put 3 guys here in my usual triangle, and those are our guys. Okay? And now we're going to look for something that looks like a median voter. Okay? And so how we're going to do it is we're going to do it the same way we did before. We have 2 policy dimensions. So we're going to split the voters with a 1-dimensional object. Which is like a really fancy way of saying a line, right? Line has 1 dimension, you go back and you forth, you got no up, you got no down, but you just got the back and the forth. Right? So we're going to split this thing with a line. Okay? So what I'm going to do is I'm going to take a line, any line, take your pick, and draw my line in. I have now split my policy space with a line. I've got some stuff, some policies off to the left. I've got some policies off to the upper right. Right? And I'm going to do this, and I'm going to move my line back and forth until I get half of the people, get the same number of people on one side as I got on the other. Okay. So I'm just going to move it back and forth, just the way same way I move that point back and forth. Move it back and forth until I get the same number. So I can move it up here. And I did not achieve the mission. Right? I got 2 people on one side, got 1 person on the other side. So I keep moving it up until I achieve the mission, which is in this particular line, is going to look like this. So once I get there, I've got the same number of people below the line as I've got above the line. 1 person below, 1 person above, and 1 person happens to be on the line. Okay? So this, and let me get the jargon right, because like if I'm inconsistent, it will definitely make your life harder when you're studying. Right? So here is what we get is is a median hyperplane. And I'll get to the hyperplane bit because, yeah, it just sounds bigger than it is. But it's a median way. We found something that gives us the median. This line gives us half below, half above. So it's kind of a median line, right, in that sense. Whereas when I put it down below, it was still a line, or hyperplane, if you're into that kind of thing. But it didn't have that median nature. It was just a line. That's the hyperplane, right? Because there was more people on one side than there was on the other. But this one is a median hyperplane because we got the same number of people on the one side versus the other. Okay. So now that we've introduced our first bit of jargon, we need to address the hyperplane thing. So for this, we got to von Neumann the thing. Well, we can't think in 5 dimensions, or at least I can't. I can tell you that for now. But we can struggle with 3 dimensions. Okay, so let's talk about 3-dimensional policy space. Woohoo! So what are we doing? We're doing what should be the tax rate. So that's we're going to think of this room. Pretend like this is a square room, right? So we got 3 dimensions. We got back and forth. We got up and down, and we got front to back, right? So let's think this way. Back and forth. This is how much taxes we should have. No taxes, 100% taxes, somewhere in between, right? Up and down is going to be what portion of those taxes we should put on social programs, right? So high, all the taxes go to social programs. Low, none of the taxes go to social programs. They go to other things, right? Okay? Fair enough. And then this way we need another policy dimension, and this will be how strongly should we work for a unified Ireland? Okay, back and forth. Right? This way, all the counties, I don't know how many counties there are, I'm a foreigner, but all the counties should be together and we should, and then over there, no, we don't want that at all, right? And somewhere in the middle, we should work a little bit for it, but it's not the biggest deal. So 3 policy dimensions: tax rate, how we spend it, and something really unrelated to taxes, at least in the short term, right? 3 policy dimensions. And then we can imagine, like everyone has preferences on these things, what the tax rate should be, and social programs, and unified Ireland, and we all have thoughts on these things, and we have different thoughts, right? And we're going to imagine that we have these same single peak preferences. So you have an ideal tax rate, and the farther you move away from that, the less happy you are. You have an ideal unification policy, and the farther you move away from that, the less happy you are, and so on. Right? And then we have to define everybody's bliss point. And let's just suppose that the population of this society is us. And where you happen to be sitting, that's your ideal policy. Right? So someone over here on the lower right, wants very low taxes. Pretty, because they're far to the left. Very low taxes. Very low social programs because they're not very high up. But they're pretty far to the front of the class, so they want reunification, right? And someone in the upper back, right, so very far corner over here, they want very high taxes, and it should all go to social programs, and screw the North, I don't like those guys anyway, right? And each person's position is giving their ideal policy. So we can imagine this class as our policy space, okay? Now, that's a 3-dimensional policy space. We have three policies. So we want to take a 2-dimensional object, which is a plane, right? Just like a sheet of paper, a giant sheet of paper, moving through the class. And we want to move it left and right until we have half the people on one side, half the people on the other side. So I take an arbitrary plane. I'm taking a vertical one. Why the hell not? I take a vertical one. Over here, I got everyone on the left, nobody on the right. Then I move it across until I get half the people on one side, half the people on the other side, and that becomes a median hyperplane. Okay? 2-dimensional object splitting a 3-dimensional space. And this is as far as I go. I can't do the 4-dimensional because of my brain. But mathematically, it's the same thing. Right? So we do that, and we split the class, and that becomes a median hyperplane. Right? Now, of course, when we're over here, so that's why the hyperplane thing. Because clearly that's a plane. Mathematically, all these objects have very similar structure: a line, a plane, a three-dimensional plane, like four-dimensional plane. These are all mathematically similar, but of course we can't imagine them. They become weird. Yeah?
Are there multiple ways to split it so you get?
Yes. Absolutely. No, absolutely. Like this is perfect. Yes, exactly. So I started out with this arbitrary stupid line, and I moved it up and down until I got half the guys on one side, half the guys on the other. But I just pulled that out of my butt, right? Like where did that come from? It's like with particular one. So we could do another one, right? We could let me get rid of this, and let me do a red one, which I'll put like so. Right? That's a line. It's got a different slope. Then I just move it up and down until I get half the people on one side. Well, same number of people on above as below, right? So at the moment, we got all three below. Here, we've got the same slope. Imagine I can draw. That we have the same slope. We've moved it down. We've got one on one side. We've got two on the other side. Not a median. Keep moving it down until we get to here. And let me... This is also a median hyperplane, right? Because we've got one guy above, we've got one guy below. And there's a million, well, there's actually an infinite number of these lines that I can draw, right? I could draw a very steep one, I could draw a flat one. There's loads and loads of them. And likewise, when I'm dividing the class, right, when we have our three-dimensional policy space, I took an arbitrary sheet of paper that was like this and moved it back and forth. But I could have taken one horizontal and moved it up and down until I got half the people below, the same number of people below as I have above, right? And that would be a median hyperplane as well. Or I could take one at a weird angle like this and sort of move it back and forth. I've got the same number of people on one side as I got on the other side, right? So in this particular example, if I do that, I got one there. If I take a very steep thing, if I take something that looks like this, that's great. I got all the people on the right, move it right and left until I get to here. That's a median hyperplane as well, because I got the same number of people to the left as I've got to the right. Okay. So this is the natural extension of our line, where we took, okay, we had a one-dimensional object, we took a zero-dimensional object, a point, and moved it back and forth until we had the same number of people on the left as we had on the right. Same thing, except with the point, there was kind of only one way I could do that. It lost track of me. Come back, miss you. Yeah, the whole thing is freaking out. Maybe if I move. Love the technology. Technology hates us. That is the way. Okay. So there was only one way to do that. So we didn't have this issue of multiple ways to do it. This is new, right? This is something we didn't have before. Like the dividing with a line is just sort of a natural extension. The dividing with a plane is a natural extension. But now there's loads of ways we could do it. Even with just a line, there's an infinite number of ways. And once we get to a plane that we're dividing everything through, there's like a bigger infinite number of ways. Like there's a slope this way, slope that way, slope the other way. We move it back and forth. Okay. So we have to sort of deal with that there's multiple ways to do this. And you can see the way I drew it here. There's multiple ways to do it. And they're not all the same in any sense. Like they're not even crossing at the same point anywhere. So what's with that, right? So we're going to do a few more definitions to see what we can say about that kind of thing, so that we can be talking the same language and understand like how general our results are in the end. Right? Okay. So I'm going to have a couple of specific examples. I'm going to start out with one where I've got four guys, and I'm going to put my four guys very specially. I'm going to very carefully put them in a square. at the corners of a square, like you'd see the dots on the 4 of a dice, right? So this is like, I didn't like plop them anywhere. I like carefully chose them because I got a plan. I know people don't think I got a plan, but I got a plan. So that's the idea, okay? And then we want to find a median hyperplane. And so if I get, let me take a particular slope. Take a slope like this and move it up and down, and I want the same number of people on one side as I got on the other side. Actually, let me not take that slope. That's not helpful. That's also not helpful. Let me start out with a flat slope like this. It'll be clearer. Okay. So I'm going to move that up and down until I got the same number of people above as I got below, right? And I move this up, and the natural thing from our triangle thing, we would naturally think, well, what about here? No, that doesn't do it, right? Because I got 2 people above, and I only got 1 person below. Okay? So even though there's the guy on the line, that's not the same thing as being above or below. Right? So I haven't achieved my goal. And I can think about if I had it way up here, again, that would not be a median hyperplane, right? Because I've only got 1 guy above, and I've got 2 guys below. Okay? But, let me do it in another color, anywhere in here, let me just do 2 of them, both of these are median hyperplanes. So I'm going to get rid of the blue. Is that okay? Okay. It's one of those things. How much to put down? Both of these are median hyperplanes because I got the same number on each side, right? You get my jargon, right? Okay. Okay. Now, we've seen this before, right? When we had our line, and we had, say, 4 guys, and then we put our point in. We could put a point here where we had 2 guys to the left, 2 guys to the right. We could put our point there where we had 2 guys to the left, 2 guys to the right. And so this having multiple lines where we can do the same thing isn't like a super shock, right? It's a thing that we had before, and we continue to possibly have that same problem. Okay, before, we call this an indeterminate zone. And in the same way, it's kind of indeterminate there. Right? Which of these lines is the appropriate one? I don't know. It depends on what you're voting on, right? So we've seen this before. But of course, we also have other slopes to deal with now. Okay. But let me do this again. Get our 4 guys. Likewise, if we have very steep lines, this is a median hyperplane, this is a median hyperplane, this is a median hyperplane. All of these are median hyperplanes where you got 2 guys to the right, 2 guys to the left. Right? So the indeterminate zone as well. But same 4 guys. Remember, I'm arbitrarily taking these slopes of the line, right? It could be any slope I want, or in fact, it has to be every slope that could possibly exist. So there's an infinite number of these slopes that I can pick. One of the slopes that I can pick is at a 45-degree angle, right? So let me maybe do this, where this is 45 degrees. That's one possibility for a slope. And I move that up and down until I get the same number of people on below as I got above. And that happens when I go through both of these points. So at that slope, there's just one way I can do it. I know it looks all wobbly. Pretend like it's a line. It looks like impressively wobbly, like I was trying to do that. Like, that would be a skill. But yeah, it's the opposite of skill, whatever that is. Now that we're in math, it's the inverse of skill. 1 over skill. Okay. So that's a median hyperplane, and in that way there's only just one. Whereas with other slopes, there's loads of them, an infinite number for an entire range, right? Okay. And I could do another thing with sort of a negative 45-degree angle. So if take this one, where this angle is 45 degrees, and that's going to have a similar thing where this is just one median hyperplane with that slope. Okay, my 45 degrees wasn't great. That's a better 45 degree. Right? So it is possible to have multiple ones with some slopes, but only just one with other slopes. Right? That's a possible thing. Which is something that we couldn't have before because it was only just one way to do it. Right? It was just take your point, move it left and right. Now we have an infinite number of slopes that we can look at and have to look at, and so this kind of thing can happen. Okay. Now, that kind of maps out the whole thing. And let me just draw it again because that's, I think, probably more helpful. So we're drawing it again. I get my 4 dots, 4 guys. Because here we get our actual jargon. So we got the purple thing going down this way. So sad. Opposite of skill, opposite. Negative skill. And what was the other color? Let's go back. The other color was blue. And so we got our blue going up like that. And let me draw in one other slope. So those are the 2 special slopes in this one. Let me draw in one other set of slopes, right, which is but you can imagine that there's an infinite number of these slopes, and they all sort of go between the guys in this sort of way, right? Yeah, but yeah, people with me, like I could draw another set that was kind of vertically, and they'd be a whole bunch of them going through there and so forth. People with me there? Okay, all right. So now we've got, pretend like this is all the median hyperplanes that a person could ever have, and this is going to make me insane. No. I give up. Okay. Okay. The people at home will just have to hear me talk and not see my beautiful face. What can you do? So we got all these median hyperplanes, but there is something special about this point here. And that we're going to give a name. It's going to be a total median. And it's a total median in the sense that no matter which slope I pick, I can draw a median hyperplane that goes through that point. It is possible to do. Okay? Now there's other ones you can see in the green, but that one point, whatever slope I pick, there is a total median. There's a median that goes through there. Okay? And through it. All right. So it's possible to do, but you don't have to do it. There's other ones that go through it as well. Now it's going to turn out that total medians are of no particular relevance to anything in the world, but they're a step in something that does have relevance to the world. Okay. Okay. So that's this. Right? We got our total median, and we're going to kind of think about this whole region where these lines are crossing. as our indeterminate zone. It has a very similar nature to that indeterminate zone that we had before. Like, yeah, probably the votes will end up somewhere around there, like, but a person in there will be on the winning side, but it's not so clear depending on exactly what you're voting for. Okay. So now we get to our analogous item compared to an item analogous to our median voter before. And here I'm going to pick a very particular set of points again. Like, I'm not like picking any random points. I'm like being very careful about this. And this time I'm using the 5 from the dice. All right, so I have 1, 2, 3, 4, and in the exact middle we got another voter. I put another voter, and I put him exactly in the middle of those other guys. Okay? And what that does is that when I have a flat slope, if I start out with a flat slope like this, before there was a whole range where those were median hyperplanes, right? But now they're not. Like if we look at this lower one, look at the lower one, make that go away. We look at the lower one, we got 2 guys below, and we got 3 guys above. So where with the 4 voters, that was a median hyperplane. Now it's not, right? Because we got the other guy. And so we have to raise it up until we get the same number of people above as we have below. And I have no idea what happened there. What you gonna do? Look, I can put my axes back. So I can raise it up like that, and that becomes a median hyperplane. Right? So now, when I have this slope, there's only one median hyperplane. Before there were loads of them, but now there's just one. Okay? And the same thing is if I take something very steep. If I take a steep thing, before this was a median hyperplane, but now we have 2 guys on one side and 3 guys on the other. Before it was 2, and that was fine. But now we got 3, and so this is no longer a median hyperplane. And so we have to move it over until we get the same number of guys on one side as we have on the other. Oh, man. I wish I need an undo here. I got no undo. Okay. I wonder what that's about. Like, I don't know what I'm doing to make this happen. So we got our guys, 2, 3, 4, 5, and our median hyperplane looks like that. And we have our other one that looks like that. And of course we have on our diagonal ones that look like that and look like that. And you'll notice they're all going through the same place. Right. So here we have a total median, but there is only one way to, like every median hyperplane goes through that total median. But there's no way to draw a median hyperplane that doesn't go through that guy. Okay? This is what's going to be called a strong total median, and that's going to be like our median voter. But we're going to leave this, and I'll come back to it next time. We'll talk about it again, because clearly I have to let you go. So see you on Wednesday.